So I first want to apologize a little bit for this change of scheduling, and I want to thank the organizers for accommodating this rearrangement. I'm going to have to leave just slightly early. I think a consequence of this is that we will miss out on the question period. I've been taking questions since I spoke this morning, and I'll continue to take questions. But I'm committing Nima, who I think will use up some of that time, to answering your questions, and he certainly has thoughts on all of these issues. And he can correct the things which I've said which may offend him. I also want to say that the notes from this morning and from each lecture will be online, and I'm actually going to use them for a minute. I'm going to turn this off shortly and switch to the Blackboard. But there are a couple of things I didn't cover this morning, and I also just want to advertise that these notes are there. Just a couple things. So a lot of what I said is here. I want to jump ahead to a couple things I didn't talk about too much. So one of the things I didn't stress, I stressed this presence of theta. Due to the anomaly, this presence of theta is equivalent in some sense to the existence of phases in the quark mass matrix. So Steve Weinberg used to have a sort of elegant way of describing this. He would say, he used a four-component language, and he would say that one of the questions in QCD is the mass matrix of the quarks gamma 5 free? So normally when we learn QED, for example, we say that we write down the mass term and we write m q bar q, or m e bar e, I should say. And you could say, well, why don't I put m e bar gamma 5 e? Or in the language of two-component fermions, why don't I write m e bar e plus e bar star e star, where m star e bar star e star, where m is complex? And the answer we would usually give is, well, we just redefine the fields and get rid of that phase, or redefine the fields by a transfer of four-component fields in a way that depends on gamma 5 and get rid of the gamma 5. And the problem there is that has an anomaly, and I just sort of indicated that here. Okay? So in general, we have that field redefinition has an anomaly, and what we actually usually say is we speak of an invariant combination of theta and the phase in the quark mass matrix. So let's see if this works. I don't know if the pointer works, but so we speak of this thing theta bar, which is theta minus the argument of the phase of the determinant of the quark mass matrix. Okay? And it's that combination, okay, which is the measure of CP violation. Now, so I also just, oh, that doesn't look good, I'm sorry. But I also indicate here, just as a little homework exercise for you, if you've never done the anomaly calculation, this is a sort of very simple and primitive version. So it's hard to see with both the Blackboard and the lights. I don't have a good figure. But here what I'm doing is saying, suppose we have a term in the mass matrix m q bar q plus its complex conjugate, okay? Or in four-component notation, that means we have an m gamma 5 at this vertex here, okay? And I calculate with two, in this case, say 2 photons, or it can be 2 gluons, okay? Calculate a diagram like this. And I've indicated that computation here, okay? It's a very simple calculation to do, okay? And it yields this anomaly, okay? I've allowed here m to be a function of momentum, rather than taking it to be a constant in space, to allow it to have some slow variation in space, or some small momentum dependence, so that momentum, otherwise this diagram actually vanishes, okay? And I've just indicated the result. The calculation is rather elementary, okay, and yields the expected result, something proportional to this phase. Alpha is this phase in the quark mass matrix, or in this case in the electron mass matrix, okay. Epsilon mu nu is this symbol we encountered before. The p's correspond to derivatives of these a's, and this is actually FF dual in momentum space. Okay? If q is 0, then p1 is equal to minus p2. Okay? And this quantity vanishes. That's why, and that's related to the fact that this thing is a total derivative. Okay? So this is the anticipated result, and I've kind of left that for you as an exercise. Okay. I also wanted to say a word or two more about the Fermion functional integral in case of the instanton. So again, a lot of these things I said about instantons are here. And I just wanted to add that I talked a little bit about Fermion functional integrals. Okay. Talked about the fact that we were interested in these eigenfunctions of d slash And in particular, we're concerned about zero eigenfunctions of D slash. So in general, we get some determinant. But we're concerned about zero eigenfunctions. And I talked about the fact that their number, okay, and quantum numbers are determined by this, by the anomaly, or one might say by the index. Okay, and I've just indicated here, for example, what these zero modes look like. It's not hard to check that these are, and again, this I leave as a homework exercise for those who are determined, to check that, in fact, these are zero modes of that solution I wrote before. Okay, so we put that together, what we find is that we have Green's functions which violate the axial symmetry in just the way I described. Okay, we have to soak up each of the zero modes for each of these fields, U and U bar, D and D bar, S and S bar. Here I've reverted to two-component language. Okay, we have to soak up each of those zero modes, so we got a non-vanishing Green's function which violates the axial symmetry in the way I described this morning. Okay? You have to do all these other things. You have to integrate over these various collective coordinates, the location of the instanton and its size. And here I've indicated, for example, what the calculation of the vacuum energy looks like. So the vacuum energy, okay, because you have to soak up these zero modes, has factors of each of the quark masses. It has a factor of cosine theta. Okay? It has a factor of the QCD scale to the B naught, the 9th power, okay, as we talked about. And it involves a d rho, a rho integral over rho, which is very divergent at large rho. It diverges like 8 powers of rho. Okay, so as I said before, we have evidence for theta dependence, but we can't do a reliable calculation. Okay, and this is related to the fact there's no, in fact, in real QCD, there's no small parameter. So we shouldn't expect to be able to do a calculation like this. But we can use other facts which we know about the strong interactions to get a better handle both on the U1 problem and the question of theta dependence. And so I mentioned the neutron electric dipole moment before. I'll just say a few more words about it. So on dimensional grounds, okay, we might expect theta violates CP. Okay, so if we have a theta parameter, we might expect a neutron electric dipole moment. How large would it be? Well, it would be proportional to theta. The characteristic size of the neutron is order of Fermi. We might guess something like theta 10 to the minus 13 centimeters. Now, we know that CP violating effects are suppressed by powers of the quark mass. If the quark mass, if any of the quark masses is 0, we can do a redefinition of the field and take advantage of the anomaly to get rid of theta. So we expect to pay a factor of quark mass. And putting that together, okay, we would guess that given that the limit on the neutron electric dipole moment is about 10 to the minus 26 ECM, so that's much smaller than this 10 to the minus 13th. I should have had an E, I did have an E there. A 10 to the minus 13th ECM I wrote before. We would guess that we need theta less than about 10 to the minus 10. Okay, and you could do a sharper estimate. I'm not going to do this in great detail. Okay, but basically the strategy of this estimate is to say that to first use say that in the presence of theta we have a CP violating coupling of the pion to nucleons, and I've written that here. So the way an older generation than me learned about pion-nucleon physics was they wrote down a Lagrangian which had a Yukawa coupling of the pions to nucleons of the kind I've written here, the first term here. Okay, this is CP conserving because the pion is CP odd. Okay, and with the gamma 5, that psi bar, that n bar gamma 5 n is CP odd. And the second term, that extra term, that g bar pi n n, is CP violating. Okay, and so one can calculate that. Okay, I'll describe that in a moment. Okay, and then using that, one can input that into a calculation of the neutron electric dipole moment. This is actually a calculation that was first done in part by people at the Institute, who are currently at the Institute many years ago. Okay, Ed Witt and Cruther and others. Okay, and their point was that that calculation, while it looks a little hokey, okay, is actually gives the leading contribution in a log of the pion mass divided by the QCD scale. And I'll draw that on the board in a moment when I get rid of the slides. Okay? But this calculation actually becomes a calculation that's reliable in the limit of small quark mass. Okay? And I think I'm just going to just stare at the result. The result looks like this. Okay? It involves those two couplings and a log. Okay? And the formula, when you work everything out, gives you that the neutron electric dipole moment is pretty much in the ballpark we talked about. It's 5 times 10 to the minus 16th theta. There should be an E, Cm. Okay? And I say this is done in an approximation which becomes reliable as the quark masses become arbitrarily small. Okay? And so again, this gives this limit that theta is less than 10 to the minus 10. Okay? So this is the strong CP puzzle. Okay? The question is, why is there this tiny dimensionless number? Okay? And this gets a little bit back to some of Nathaniel's remarks. Okay? In particular, this way that a 't Hooft formulated naturalness. And I think this is, I forget whether this was what Nathaniel called technical naturalness or whatever, but this is sort of the case. We're not making a theory of this. We're just asking, is it okay? Does it bother us? And at some level, you might say, yes, okay, because as theta goes to 0, the strong interactions become more symmetric. They preserve CP. But nature doesn't preserve CP, okay? And so we might expect the effects creep in. Okay, one of the things Nathaniel said, and I will come back to this, is that the radiative corrections are, in fact, in the standard model, quite tiny to theta. So if theta somehow is set to 0 in some way at some high energy scale, the corrections are extremely small, and I'll do a little estimate of how that looks. Okay, and maybe that's enough, and maybe we shouldn't lose too much sleep over this, but I say we'll talk about that a little more. Okay, but I want to make this other remark that among naturalness problems, the strong CP problem is special in that it is almost of no consequence. And here I think I'm channeling, is Nima here? I think I'm channeling Nima. Okay, so, who will say, well, maybe it's all anthropic. Okay, see, I can blame it on Nima, and I don't have to take any credit for invoking that. But theta is special in the sense that we pretty much don't care. Okay, so apart from the fact that the neutron electric dipole moment is so small, small theta, theta being 10 to the minus 3 or 10 to the minus 9th would not affect in any appreciable way the world around us. It would not affect nuclear processes in stars. It would not affect things going on the Earth in any significant way that we can think of. Okay, so there's something special about theta. It's very small, and it sort of seems like we better find an explanation for it. Okay, so I want to say that kind of to There are, and that's an interesting question. And if I were giving the naturals, there's a good reason. I say I'm an old guy with who's had lots of wrong ideas about the hierarchy problem, so that's why I was not asked to give the hierarchy problem lecture. Okay. So I'm just going to conclude this part with the slides by just saying, as I would have concluded this morning if in another half hour, that so there are 3 possible resolutions which we're going to discuss now. We're going to try and assess. One is the possibility that mu equals 0. Okay? In that case, we could do a chiral rotation. I've written in now 4-component notation, which eliminates theta from the Lagrangian. Okay? And then, okay, that's not consistent with facts we know from current algebra, okay, from features of the meson spectrum, for example, which lead to an estimate of the mu of the sort we talked about this morning from lattice gauge theory. Okay, but people have argued through the years that maybe those effects are effective mu would be generated, and I'll describe that in a little bit. Okay, and lattice computations have pretty much nailed that door shut, but we'll talk about that a little bit. Another possibility is that the underlying theory is CP conserving, that CP is exact, and CP is spontaneously broken. Okay? The delicacy there is that if CP is spontaneous, CP has to be spontaneously broken in a way which generates a CKM angle, okay, which is large. The CKM angle, as I'll remind you, is about 1.2. Okay? And so we have to explain that while not generating a theta that's larger than this 10 to the minus 10. Okay? So Ann Nelson and Steve Barr propose models which might do this, and we'll talk about those a little bit. This is a plausible framework. Okay? And a third possibility is a light particle called the axion, which dynamically cancels off theta. Okay? And I'm going to try, in the spirit of the brainwashing that Nima was arguing against this morning, I'm going to try and argue that only the third possibility looks terribly plausible. But we'll see, and we'll see if I convince you. And these are real questions in terms of directions in the field as a whole. Okay, which of these possibilities is correct, or some fourth possibility that would also be exciting, is a sort of question we would like to deal with. Okay, so we're on now to lecture 2. Okay, and so just to say what we're going to do, I'm going to talk about these various solutions. Okay, I'll talk about mu equals 0. Then I'll talk about this remark. I'll echo this remark of Nathaniel's and talk about the size of radiative corrections in the standard model. Okay, and then possible ways of understanding why theta might be small, so that we could realize this idea. Theta is small; it just gets little corrections. Okay, and that's this framework of Nelson and Barr. Okay, and then I'll turn to axion physics and some basics of axion physics, and if I have time, I'll end with a discussion of the astrophysical constraints on axions. Okay, so I'm going to switch now to the board. Everything is like magic here. Oops. Okay, so again, looks like I have some of Neil's notes. So let's see, I want to get this thing again. All right, so I want to talk about these 3 solutions. Okay, so I'll start with the mu equals 0 solution. Okay, so I want to sort of think a little bit about what this means. Okay, so first of all, if mu equals 0, as I said, what does that mean? That means if we look at the Lagrangian, we have things like md v bar d plus ms s bar s, but no term for the u. No term for the u, and here I'm going to use 2-component notation. So I'm going to add here plus the complex conjugate. Okay, and in this story, what I'm worried about, well, I don't have to worry about anything here. What I can say is, if I have some theta, f of dual, okay, then I can do a rotation, a chiral rotation. I can let u goes to e to the I theta u. Okay, I'm not going to worry about the sign, and as I said, I'm not promising you I get the factors of 2 right. Okay, and the change in the Lagrangian under such a transformation is theta partial mu j mu. This is a general thing we learn in our first quantum field theory course about symmetries. Okay, that if we have a symmetry, or if we have an approximate symmetry, if we consider the symmetry transformation, we have the change in the Lagrangian is the parameter of that transformation times the divergence of the current. This is the thing we said is theta over 32 pi squared ff dual. Okay. Okay. So I probably want to put a minus here, and so this is a minus. Okay. So we can eliminate theta from the Lagrangian if the u quark mass is 0. People choose the u quark because it's believed to be the lightest quark. This actually gets to one of Nathaniel's remarks this morning about radiative corrections to things like the pion masses. One of the things that's kind of amusing is that the u quark has the bigger charge. It's the lighter quark. Okay, so you might have thought, well, bigger charge, it should be heavier. Okay, okay, so that's good. Now what do we really mean by that? Okay. So again, as I mentioned in the morning, if I tell you the value of the U quark mass, for example, I mean the U quark mass at some energy scale. Okay, so what I really mean is mu at some scale. I'm going to call this lambda Sm, and it's going to recur. Okay, some scale, maybe that's 1,000 TeV. Choose some number. Okay, and what I mean by that is that at that scale, this mu, well, it's not really going to be literally 0, but less than or equal to some number, and that number turns out to be something like 10 to the minus 10. And the reason goes back to the formula I flashed kind of quickly on the board, which was that the neutron electric dipole moment was some number, it was theta times some number times something which went like mu over mu plus md. Okay. It's something which goes to 0. The effect better go to 0 as mu goes to 0, and indeed it does. Okay, and I just sort of indicated that here. Okay, so this is mu, not md. Okay, and so what I actually need is that mu over md at some scale, at this high scale, should be less than 10 to the minus 10. Okay, in that case, according to this formula, the neutron electric dipole moment will be small enough. Okay, now, but in fact, there will be an effective mu, okay, and an effective mu which arises from instantons. You can think of as arising from instantons. So I'll say instantons, or we can think of this, since as I've kind of argued, you can't really do instanton computations. More abstractly, I can think of this as arising in the language of the chiral Lagrangian. But let me just think about it in terms of instantons. What do I mean by that? This will allow us again to illustrate some features of these instanton computations. Okay, so I'm going to think of an instanton. I'm going to do something which people kind of do in this story. They kind of draw an instanton as a kind of blob. I'll put I here for instanton, but usually they don't label it in any way. Okay? And the thing about the instanton is associated with these fermion zero modes. Okay? So for light quarks, there's a zero mode for each flavor of quark. So there's here for U bar, D bar, S and S bar. Okay, so there's a light mode for each of these quarks. Okay? When I wrote down before, when I flashed that slide, okay, that showed E of theta, okay, the way I got that was I took this and I said, let's perturb with the quark masses. Okay, and by that I just mean when I do my path integral, okay, my path integral, I have this is some product of eigenvalues of d slash, okay, of the fermion, of the Dirac operator, okay, and I have these zero modes, but once I include the masses, the eigenvalues are no longer 0, they're of order of the quark masses, okay, because the operator is no longer d slash, but it's d slash minus mq, okay, yeah.
Sorry.
Absolutely, please.
The reason you can do that kind of rotation only in the case mu equals 0, is it because you only rotate u and not u bar?
No, it's not so much that. It's the fact that the quark mass itself, the quark mass term, the mu u bar u, is not invariant under that rotation. Okay, so that was the statement that I can absorb the phase, the theta, into the quark masses. Okay? If there is no quark mass, then I'm free to do that, and I don't change anything else in the Lagrangian, other than the theta term, other than the theta f of dual term. Okay? Any other questions? Okay. This is, one reason I posted the notes. This is a lot happening in a few hours, but this gives you access to a lot of physics. This instanton story and this anomaly story, and if you're not familiar with it, it's good to sort of start becoming familiar with it. Okay, and there are a lot of little exercises I've suggested in these notes, a number of little exercises for those of you who are determined. Okay, so in this case, as I say, we perturb with the quark masses. Okay, that means that the lambda for the U quark is of order mu, the lowest eigenvalue lambda for the d is of order md, and so on. Okay? And this was the origin before of this expression I wrote that E of theta went like something like lambda, this was for 3 flavors, went like lambda to the 9th cosine of theta times mu md ms. Okay, that was ms. That's coming from these lowest eigenvalues. Okay? And I can think of this in terms of sort of tying these up. So people will draw the diagram sort of like this, where they tie up these zero modes with the mass terms. Okay? mu md ms times some expression which unfortunately was divergent. We had something which went like d rho, and I believe it was rho to the 7th. Okay, yes, rho to the 7th. Okay, so we had an expression sort of like that. By the way, that number rho, I'm not being so smart. I'm just getting that from dimensional analysis. Okay, the real calculation involves some work, but this is the output with some coefficient. Okay, that was what we had before. In this case, where the u quark mass is 0, okay, I can't close this up anymore. But instead, what does this look like? Out here comes a u and a u bar. I've closed this up. This is like a mass term for the u quark. Okay, I have a u and a u bar, a 2-point function with the u and the u and u bar quark. And so what I can draw, instead of this E of theta, I can replace this by m. The theta is gone. Okay, I have md ms. Okay, and I have some divergent expression. Okay, I probably have the dimensions wrong also. This is mass. Okay, this is mass to the 9th, 10th, 11th. Okay, so I need this to be 9, so this is rho to the 8th. Okay, I still have an expression that's very divergent. I don't really know how to compute it, but what people said, this goes back to Georgi and to Kaplan and Manohar, they said, what this suggests is there's an effective mu which goes like md ms, okay, over the QCD scale. Okay, and they said, well, ms is 100 MeV or so. The QCD scale is 100 MeV or 200 MeV. Okay, so this is like half the d quark mass. Okay, so that they said, that's pretty good. The u quark mass could be 0. Okay, at some high scale, and effectively it would look non-zero, kind of look like what we see. Okay, so they said maybe this is the explanation. Okay, so before saying why it's probably not the explanation, okay, let me say why would you believe in a crazy idea like this anyway? Okay, so people often look at you when you say this and they say, oh my goodness, this is actually I just get rid of this. That this, why would you do this? Because why should the u quark mass be so small? Okay, because the u quark mass, after all, is corrected. This is kind of in the spirit of Nathaniel's lecture this morning. Okay, you say, okay, if the u quark mass is 0 at some scale, it gets some correction, now not from Feynman diagrams, but from these instantons. Okay, and so why does it make sense? Why would that make sense? And I give two answers to that. Okay, just sort of from experience. So we also heard a little bit about these Froggatt-Nielsen models from Nathaniel this morning. Okay, and in fact, I think Nati may have left, but Nathan Seiberg and Yossi Nir and others, in fact, explored a variety of models which gave, I think it's Lure, Nir and Seiberg, and I don't have preprint numbers here. I think when this paper was written, the archive barely existed. But in this paper, they made models of this Froggatt-Nielsen type, and they found frequently mu in models for the quark mass matrix. Okay, so that's one example. Okay, and again, that statement is a statement about some high-scale theory. Okay, there will be corrections of this instanton sort. So this was an implementation of this kind of idea. And I should say more generally, and I'll credit myself for this, in string theory, we often encounter discrete symmetries which are anomalous. And by that I mean they're broken by instantons. So they go like e to the minus 8 pi squared, masses, I should say, go like e to the minus 8 pi squared over g squared at some high energy scale. Okay? So they're not 0, okay, but they can be very tiny. Okay? So this combination of things makes this idea not look so crazy. Okay? And the main problem is something I alluded to at the beginning, that in fact, from lattice gauge theory, I wrote down a number for mu, but lattice gauge theorists find that mu is something like 2.5 MeV with an error of about 10%. Okay? So in other words, about 10 standard deviations from 0. Okay? So in the lattice gauge community, this is viewed as a settled question. Okay? I should say that, and I probably would like the recording equipment shut off or something at this point, that I'm just slightly skeptical about the quality of this error bar. Okay? And I think I'm in a small minority, but not a minority of 0. And in fact, I myself and others have proposed various tests. In fact, I called it a calibration of the lattice computation. And I'm not going to talk about this at length here, but this, in the spirit of the fact that in the 2 hours I've talked so far, I claim I've given you all kinds of tools. Okay? These are papers at this point you could read. They're not that deep. They don't involve doing much more than calculating things like what I've described up here. Okay? But in fact, in general, if you look at lattice gauge theory papers, I don't think there are any lattice theorists here, but if you ever look at these papers, when they calculate things, they're kind of results. But the errors are determined sort of self-consistently. People vary the volume of the lattice. They vary the couplings. They vary the lattice spacing. They ask how much, but they don't have, it's not like, I thought I'd like to compare it to experiments. I mean, I sit around and talk a lot to experimentalists. And if you have a detector, okay, you don't just sort of stick it in the beam and say, well, I've done a lot of Monte Carlo and I'm sure I know what's going on. Typically, you go and you take it to a test beam and you see how it works and you see if your error estimates were good or not. Okay, and I'd like an analog of that. Okay, and I claim that there exist such analogs. There are things you can calculate, okay, and you can, which are comparable to, in their difficulty, to the calculations of the hadronic spectrum, the kinds of computations that give you these quark masses. And so if you're willing to spend a few $1 million and a few years of your life writing code, you can check this and check your errors. Now, you might have, again, since the sound systems are off, there are some lattice theorists who have expressed some interest in some of these, but it is a big investment in time and money, and it's not created a mass movement.
The lattice computes the effective mass, or there is an effective mass which is in agreement with experiments, right?
The lattice computes an effective mass at a scale. So the lattice, so just think of the lattice as a thing, right? You do this path integral, okay? And you have some parameters. You have a coupling constant, you have quark masses, okay? And you have a scale. You have an A, which is the lattice separation, and a G, and this coupling G, so G is G at that scale. And now you just, you write your code, you compute. Okay? And the way you check things is you check things like, well, it better be true that if I compute, say, the mass of the proton, okay, as I vary the lattice spacing, if I vary A, okay, the proton mass better not change, and the way you fix that is by changing G. And G and A, if G is small, should change in the way governed by the perturbative renormalization group.
Apart from the error, the lattice calculation should in principle also include non-perturbative effect.
Oh, it should have everything. Oh, yeah. Oh, absolutely. It should have that in it. So the claim is that the effect of Kaplan and of Georgi and Kaplan is not large enough to account for the effects we see. So that's the statement, and you'll find that statement very clearly made in the lattice literature.
So I'm just confused. MD over 2 is like 2.5 G, MEV, right?
Yeah.
So isn't that in perfect agreement with what lattice is finding? So I don't understand
No, because Lattice is finding the value at a high scale. I want to know the value of those parameters at relatively low scale.
I see, okay. So the
Right.
value
So I quoted this morning, I said at 2 GeV. Okay. In some cases, these calculations are even done at higher scales. Okay. So the state of the art is pretty impressive. Okay. So all this kind of hinges. So there's a whole story which hinges very strongly. We could debate whether and we will debate whether the axion is more plausible or less plausible than mu equals 0. Okay, abstractly before you compare with experiment. Okay, but the stakes in this lattice computation are that the lattice computation claims to rule out the axion mass. Now I should say, by the way, that this is my personality. Okay, the axion gets discovered. My dean will be very proud of me. All kinds of things. So it's in my nature I'm somewhat ordinary, and my ideas must be wrong. So I'm not willing to give this up so easily. Okay, but I say if you have friends who are lattice gauge theorists, I think they'll mostly look, and if you tell them this, they'll look and they'll say, "What's he talking about?" Because they're pretty convinced that this is okay. So I mentioned this work. There's also this story is myself and Guido Festuccio, who was actually for a while at the Institute, and some students of mine, and another person very interested in this question is Ryuichiro Kitano at KEK in Japan, who is also pursuing issues related to these questions. And there are a lot of interesting theoretical issues around this. And sort of in the spirit, I think, of some of our lunchtime conversation and so on, in terms of shopping for what are the interesting problems now, there are many interesting problems, but I think this class of problems is interesting, and it's certainly associated with some of the dark matter issues we're going to talk about in Neil's talks and so on. Okay? All right, so I feel like there was something else I wanted to say about mu equals 0, but basically that's, I think that's enough. Okay, so that's kind of the story there. All right, so that's one solution of the strong CP problem. So I want to now turn to this idea of spontaneous CP violation. And to first do that, to do that, I want to give a setting for that, I want to talk a little bit about this comment of Nathaniel's that the radiative corrections to theta are really, really tiny. And they are really, really tiny in the standard model. Okay, so when you see this, you might almost say, what are we talking about? And a name that comes up in this story is a name that came up already this morning, Marie-K Gaillard, along with John Ellis. In the early days of this question, asked just how big are the radiative corrections to theta? And I can ask this two ways. I can think about quark masses, or I can think about Yukawa couplings. So if I think about Yukawa couplings, I'm thinking about renormalizations over long scales, renormalizations of dimensionless couplings, and I'm going to focus there. So if you like, I'm going to look for ultraviolet divergent corrections to theta. Okay, and how do I do that? Well, remember what we said is that the observed theta is this thing called theta bar, which is theta minus arg determinant m. Okay, so what I can do by chiral redefinition of the fields is I can put theta completely into the mass matrix. Okay, and that's what Gaillard and Ellis did. Okay. Okay, and then they went further. They said, let's suppose that theta is 0 once I've done that. In other words, suppose there's no theta FF dual and there's no phase in the argument of the determinant of the mass matrix. Let's ask what do radiative corrections do? Okay, and so let's think about that a little bit. Okay, so I don't know, determinants, since high school, determinants have made me nervous, and phases in determinants make me slightly more nervous, but they're not really that hard. Okay, so if we think about what are we interested in, if we think in terms of the Yukawa couplings, okay, what we're asking about is the argument, the phase in the determinant of yu the Yukawa couplings of the U quarks thought of as a matrix, okay, times yd. Okay? And let me write that as determinant yu naught plus delta yu naught, delta yu, times yd naught plus delta yd. I think I want to do as a capital, okay? All right, so I just, again, this is some elementary linear algebra statement. So we're interested in some product, okay? And then what I want to do here is I want to expand the determinant or the log of the determinant okay, so what we're interested in are theta, our effective theta is equal, since yu and yu naught and yd naught by assumption had real determinant, okay, then what I'm interested in is something like yu inverse, let me get this right, yu inverse delta yu plus yd inverse delta yd. The sort of the leading diagnostic for this phase, okay, will be an expression like this. Let me make sure that I'm writing this correctly. I think so. Yeah. Yeah. Okay, so let's think what that looks like in terms of Feynman graphs. So what I'm worried about, okay, basically this problem is going to come from the Yukawa couplings. Okay, it's the Yukawa, so the assumption is the Yukawa couplings certainly have phases, even though this arc determinant is real, okay, there's a CKM angle. Okay, that's the issue. The issue is how is the CKM angle getting into this story, okay? And normally that's a hard thing to think about, but in terms of these matrices, it's going to be relatively easy, okay? So let's think about what kind of Feynman diagrams we're interested in. So here's an example. We could have something like I'm going to do this in two-component language, so I can have a quark doublet coming in, right? I can have I'm sorry, I want to draw a solid line here. Okay, a quark doublet coming in. Here's my Higgs, phi coming off. I have another Higgs I'm exchanging. And here I have, for say, maybe a U bar, then a Q, okay, and a U bar. Okay, so this is a correction. This is a piece of delta yu. Okay, it's a correction to the U quark Yukawa coupling. Okay, and what it's proportional to is y u. Let me make this right. Dagger yu. Okay, it's a matrix. Okay, it's a matrix, but it's a Hermitian matrix. Okay, it has some nice properties. So yu dagger yu is the dagger of that is yu dagger yu. Okay, so this is Hermitian. Okay, and I can draw similar things with d quarks. Okay, and gradually I can draw things that get more and more complicated. So let's do this here. Yeah, we don't need that anymore. Yeah.
So initially you put you rotate all the theta bar to the determinant.
Right.
But I mean, in principle, you would have to do it at every step in the running, right? So
No. I'm assuming at some scale. So the spirit of this is I'm assuming that at some scale the argument of the determinant is real.
you would also consider correction not only to the Yukawa coupling but also to FF dual directly.
Well, I'll leave that for you to think about a little bit. At the level of Feynman diagrams, you won't have those. Okay, and that was kind of what Ellis and Gaillard were exploiting here. So, and that's basically related to this fact that FF dual is a total derivative. So, okay, so now that Nati's come back in, I can hide his name. Okay, so what have we got here then? Okay, so we can draw progressively more complicated graphs. The one I've drawn here is going to give something in the form is just giving delta U is, remember, I have here, just to note, I have yu dagger yu, I have one more yu, okay, but that got canceled by this yu inverse here. Okay, this is one trick with determinants. Okay, so delta theta here, this contribution goes like trace of what I'll call A, and here A is yu dagger yu. Okay, and that's real because A is Hermitian. Okay, so that's a real, so I'm sorry, I should write imaginary part of this. It's the argument of it, or it's the, right? So that's real, so we get no, that trace is real, so we got no contribution. Okay, and we can keep going. Okay, we can start drawing more and more complicated diagrams, things like this, and so on. And all these things are all of the form trace of products of things like A, B, A squared, and so on, as we draw more, where A is the thing I wrote, it's yu dagger yu, and B is yd dagger yd. Okay? And now you can ask, what is the, if I have a product of Hermitian matrices like this, when is that trace complex? Well, it turns out you need a whole bunch of them, and I always have to remember what it is. Okay? Okay, so yeah, so the simplest things that are complex are traces with 6 of these matrices A and B. Okay, so this is probably some theorem that mathematicians know how to know in their heads or something. This is something I have to sit down and just, draw lots of, write down lots of products and check. Okay, but I guess I can put this here. But the simplest sorts of things are the simplest ones are things like trace of AB. I hope I've drawn this right. You guys can check me. A squared, B squared. Okay, this is an example of something which you, when you take the complex conjugate, you Hermitian conjugate all the factors, you don't get back what you started with. Okay, so this is something with 6 of these. This corresponds to a 6-loop diagram. Okay, so I need 6 loops with Yukawas, and Yukawa couplings, except for the top quark Yukawa coupling, are small. So this is incredibly small, and it turns out this one's still 0, okay, because this one, the diagram where I have the A's and the B's is canceled by one where I switch the roles of B's and A's. To fix that, I need, and this is the point, one of the points that Ellis and Gaillard made, I need to add one more gauge coupling. I need to add a gauge coupling. I need one more loop. So actually, I need 7 loops. So when we say things are small, they're really, really small. I don't remember. At some point, I estimated what this is. It's really tiny. Okay? It's some really tiny number. It's not just that it's like one loop suppressed in one set of Yukawas. It's really tiny. So this problem, so a person could stare at this, and I'll just leave you to, in the spirit of not trying to prejudice you too much, I'll leave you to ponder it, but these radiative corrections are small. So one could say, well, suppose I could just account for y at some scale, the unification scale, a little below maybe or something, why this effective theta is 0, okay, and all I had below that scale was the standard model, then the corrections would be infinitesimal and I wouldn't care. Okay? So this is something to sort of keep in mind with this problem, and as I say, it dovetails with some of the things that Nathaniel said this morning. So let me try and give you a kind of setting for that. So this is, okay. So again, this sort of dovetails with some of Nathaniel's remarks of this morning, because this is a kind of weird way, solution of a naturalist problem. We're going to look at this proposal that CP is spontaneously broken. Okay. In such a way that we generate a CKM angle, but at the same time generate a small theta. So let me just write down a version of this model that Nelson and Barr wrote. Okay, this is a little bit streamlined of something that they wrote originally. Okay, so I consider adding to the standard model a set of a vector-like set of fields. Okay, so I've used little q for the standard model fields. Now I'm going to change the notation a bit. Okay, and I'm going to use little q for these vector-like fields. So I'm going to write a mass term mu q bar q, okay? All right, plus lambda ij, eta I d bar j. These are the ordinary d quarks. These q and q bar are this new vector-like set of quarks. Vector-like means that I'm allowed to write a mass term for them. Okay, they have suitable quantum numbers that I can write a mass term. Again, I'm using two-component notation here. Okay, and then I have plus y. These are the usual Yukawa couplings. YFG q d bar q bar f d bar g. Okay, phi. Okay, so phi is the Higgs doublet. I'm just thinking about ordinary theory with one Higgs doublet. Okay, standard model. Okay, the D's are the anti-D quarks. I have, and the U's. And I'm assuming the U quark is just the usual thing. There's no analog of the Q and Q bars for the U's. The Q and Q bars are charged plus or minus a third. Okay, and I am not adding a plus or minus 2/3 charge. You could try variants on this where you do this. Is just a kind of simple version of this. And what does it mean that CP is a good symmetry? It means in two-component language, CP is a symmetry if mu and these lambda ij and yfg are all real. Okay, so in two-component language, CP is really simple. CP basically just complex conjugates the two-component spinors. Okay, so, all right, so this is a partial implementation of this. Now, what I need to break CP then, what I need is these etas. So I didn't tell you what these etas are. These etas are some scalars. Okay, they're scalar singlets. They don't carry SU2 or U1 quantum numbers, and I feel like I left something out. Yes, I left out Q. Okay. Okay. So remember, this is charge minus this is charge minus a third. This is charge 1/3. Okay. So the charges add up here, or the hypercharges add up properly. Okay. I'm sorry, I left out. That's an important piece. Okay. So this is something that generates. So this is sort of looks like the ordinary mass term for quarks. This is some additional term. Okay, these etas are going to be some scalars. Okay, we're going to assume they have expectation values, and we're going to say that these lambdas are expectation values. Etas, excuse me, have expectation values. So these are some numbers. Let's call them Ci or something, not equal to 0. Okay, and we're going to assume they break CP. Okay, which for scalars basically means they're complex. Okay, so we're going to assume that they break CP. All right? So this gives rise to a mass term for these D quarks. How does it look? Let's put it here. So the mass term has various pieces. If I think of this as acting on the Q and the D bar, it's got a term mu. Okay, this mu is real. It's a dimensionful number. Okay, it has in the bottom corner it has 0. I'm sorry, it has MD. Okay. Okay, so this is acting on Q and D, for example. Okay, and as a column, and on the rows, it's acting on Q bar and D bar. Okay, and then there's a 0 here, and something I'll call B here. Okay, where B is like a vector, Bi is lambda ij, eta j, in general is complex. Okay, and if you diagonalize this, you get some messy thing which is complex, but what you can see right away is the determinant is real. So this is the mass matrix, and call it MD, and the mass matrix of the determinant of MD is real. And again, as I say, I have a hard time with determinants, but I have zeros in the left-hand corner, and and the only complex numbers are over here, so I know that I get something real, a real determinant from this. Okay? So this is basically the idea. The idea is, okay, I've set up some structure, okay, which happens to do what I want. It happens to give me a CKM angle, in principle, which can be of order 1, okay, and at the same time, it gives me 0 theta. It gives me the argument of the determinant of the mass matrix is 0. Okay, so this is the idea. Okay, so it's okay, but there are a number of things that might bother you about this. Okay, I should say, for starters, again, I should stress this fact that if this is how things work, it's pretty weird from this naturalness perspective. Okay, because sort of unlike the kind of things that we heard about this morning from Nathaniel, okay, there's nothing light that signals this. The etas don't have to be light, they're just some heavy scalars. Okay, the Q and Q bar are heavy because of this mu. Okay, there's no low energy signal. Okay, other than the fact that theta itself is small. It's true, it's kind of neat. Okay, if it's how nature works, maybe it's neat, maybe it's not. I mean, in a sense, it's bad because it means it's hard to test the idea.
So when you say that the VAV beta breaks the CP, does that mean that the VAV is complex?
Yes.
Now, another question then is that you're saying that the determinant of the MD is not real, but the effective theta parameter is going to be theta from the FF tilde plus the arithmetic determinant of this thing. Now,
No. Important point here. We're stressing, because CP is conserved, okay, and this is something I may say a word or two about a little bit later, but because CP is conserved by assumption in the bare Lagrangian, there is no theta in front of FF dual. Okay, I'm sorry, I should have stressed that. So in addition to this, so as I said, this parameter has to be real, these parameters are real, these parameters are real. Okay, in addition, there's no bare theta. Although that would also break CP. That would explicitly break CP. I didn't even rotate it. It just isn't. It just can't be there. It's just not allowed. Okay, and that's kind of the rules. Okay. Well, maybe I will actually have a little aside here. For a long time, I didn't know what this meant. In a sense, like, who tells me what the bare theta is? Like, I didn't kind of know where that came from. And then along came string theory, and in string theory, there is a well-defined notion of what the bare theta means. Okay, so the thetas are determined, in fact, by some fields which look like axions. So they're secretly axions in this story. Okay, and what I mean by the bare theta being 0 is somehow those axions are such that the coefficients of the FF dual terms vanish. Okay, and whether that's, I had some slides which I erased because just there isn't time, but whether or not that's a plausible thing is something worthy of thought. Okay, so there are lots of questions. I hope the spirit of this is everything is perfectly clear except for the questions which are good research problems. Okay? Probably, I'm sure I'm not achieving that level of clarity, but a lot of these questions I think are questions which are open, which are things which are worthy of thought. Okay, so all right. So at this point, okay, what might bother you? Okay, I'm going to talk about a few things in these notes which I showed you. There are more. Okay, but let me mention a couple things which might bother you here. Okay, so one is we need several etas. Okay, why do we need that? You can check if we just have one. Okay, then well, it's obvious in a sense. If I just have one eta. Okay, then any phase in eta I can get rid of by a redefinition of Q. Okay, so I need several etas. Okay, and I also need that the eta i's, or really these Yukawas times eta i's, what I would call them, these lambda etas, have to be comparable to each other and to mu. Okay, and why is that? Okay, that's because as I keep stressing, the CKM angle is a number of order 1. It's 1.2 or something. Okay, so if, for example, if the lambda etas are all much smaller than mu, okay, any CKM angle is going to be really tiny. It's going to be suppressed by lambda eta divided by mu. Okay, so in fact, we already need several things here. okay, which are kind of troubling from, again, from the point of view of the things Nathaniel talked about this morning. Okay, we need to have several scalars. Okay, they all have to be comparable in mass and not too heavy. Okay, and they need to be comparable to this parameter mu. Okay, mu itself might be an expectation value of a field, but then that's one more scalar. Okay, and one more scalar whose vev has to be comparable to the vevs of a bunch of other scalars. Okay, so there are a bunch of things going on here. Okay, and this sort of story starts to look tuned. If we're bothered by the Higgs mass, okay, even if this scale is near the unification scale, several scalars near the, that's sort of like a tuning, again, of a very significant tuning, much worse than the problem we're trying to solve, this 10 to the minus 10 we're trying to solve. Okay? And things get worse when we look at radiative corrections. Well, actually, I should say things first get worse when we look at higher dimension operators. So I think I'm just going to make a list here and make some comments. I'll let you look a little bit at these notes if you're really curious to see some of the details. But let me at least write one of these down.
Can I ask
Of course.
So just to understand the logical achievement of this solution to the strong CP problem, let's say that we found that CKM CP phase is actually 0, turned out to be 0. Then would I be say that the Yukawa is all real, and I don't have data from the beginning? Would there be the same level of a solution to the strong CP problem compared to this?
If we didn't have a CKM angle, with the strong, we would to the extent we lose sleep over the strong CP problem, we wouldn't lose sleep over the strong CP problem. And there have been moments when it looked. There was a brief moment in the early part of the millennium where some experimental results suggested maybe the CKM angle was 0 and CP had to come from someplace else. And, and maybe there would be some other way of understanding. There are various directions this might have gone, but at the moment, we know the CKM angle pretty well. And so this problem is, in the form I'm describing it, is a real problem. Just to mention some other things, we might have higher dimension operators. So I'll call this 2. So I might have things like eta I, eta j over, say, m Planck or something times, let me make sure I put the indices where I want to put them. Yeah, times q bar q. Sorry. Okay. So I might have terms like that. Okay. Term like this would be like a phase in mu. And remember, we're trying to account for a number which is 10 to the minus 10. Okay. So, and we already said that eta is comparable to mu. Okay. So this, for example, restricts the scale at which the phenomenon can occur. And if I accept that, that means the scale is relatively low. Okay, that makes these tuning problems worse and the question of coincidence worse. And there is a history of looking at radiative corrections. And I think I'm just going to say here that these are problematic. Okay, they tend to be large as well. Okay, you need to suppress so I talked about radiative corrections within the standard model itself, and I said those are really small. Okay, but the radiative corrections here are potentially large. Okay, so there are a lot of reasons why. I told you my goal was to brainwash you that the idea that the axion solution is the solution, and so in that spirit, there are a number of these problems. Now, with supersymmetry, you might hope that some of these things would get better, and they do, but not infinitely better. Okay, so one of the things about supersymmetry is we're not, And this doesn't have to be supersymmetry at the weak scale. This could be supersymmetry a little below the gut scale or something. Okay. And with supersymmetry, the light scalars don't bother us. Okay. We still have coincidences. Maybe they're not as scary as the coincidences in the non-supersymmetric case. So I could say here scalars are okay. Okay, some of these operators are absent. The one I written here is absent, for example. So some ops are okay. Okay, and the radiative correction story is somewhat different, but still problematic. And basically the reason for that is in addition to the kinds of couplings I've described here, we also have soft breakings of the supersymmetry which can carry phases. Okay, so we have a whole set of issues that we have to worry about here. Okay, so I would say I wouldn't totally write off this story. I say I didn't totally write off mu equals 0 because, okay, maybe somehow the lattice results aren't entirely reliable. Okay, and I won't entirely rule this one out either, but it also looks troubled. Okay, all right. So with that, we're ready to go on and talk about axions. Or this idea of a Pachequin symmetry. Okay. So the Pachequin symmetry has an interesting history and was presented in a particular way originally, but we could say it in a kind of more general way. Okay? In general, what would we like? We have this term theta FF dual in the Lagrangian. Okay? And what I'd like to do is get rid of theta, and the way I'm going to do that is I'm going to say let's look at theta, let's modify this term and replace theta over 32 pi squared by theta over 32 pi squared minus FA, minus some field A divided by FA. So A is a canonical scalar field. It has dimension 1. FA is a number with some parameter. Okay, FA over FA times, and I'll put, I think I want 32 pi squared here too. FF dual. Okay. And in this way, okay, well, I can get rid of theta right away, right? I can just redefine the field A. A goes to A plus theta. I may regret this minus sign. Okay. But that gets rid of theta. Okay. And now the question is, what is A? Okay. So it doesn't really, by itself, this doesn't solve the problem because you have to ask what A is. Okay. But if A equals 0, if let's do it this way, if then A equals 0, okay, then the effective theta is 0. Okay, and we've solved the problem. Okay. Now, what's important here for this to be true? So, what determines the expectation value of A? I should really write this with brackets. Okay, what determines the expectation value of A? Well, in general, we might have some V of A. Okay, and what I just and you might say, well, I haven't solved any problem because I say my underlying theory doesn't preserve CP. Okay, so why should V of A? So the CP conserving point is with this redefinition of A, the CP conserving point is the point A equals 0. Why should that be favored? And what Pachequin supposed in this language was that V of A is equal to 0, okay? Not quite, but let's start with that. V of A is almost 0, okay? And that means that there's a symmetry. The Lagrangian has a symmetry under which A goes to A plus a constant, okay, which is violated only by this coupling to FF dual. Okay? And that's a thing called the Pachequin symmetry. So what they postulated is actually something kind of weird. Okay? They said, there's a symmetry which is a good symmetry except for this stuff in QCD associated with instantons, or whatever you want to call it, this anomalous symmetry. Okay? So that's the proposal. Okay. If this is the case, if the only thing that violates the symmetry is QCD, is the effects of QCD, then I've lost my poll. Oh, there it is. Thank you. Okay. Okay, then the minimum, in fact, it's easy to see that A equals 0 is a stationary point. And that's basically because if I now think of my theta effective as being this A over FA, okay, then under CP, theta goes to minus theta. Theta effective goes to minus theta effective. Okay? And what that tells us is that the potential for theta, or A, is an odd function. Sorry, it's an even function of theta. I'm having trouble with my high school algebra, linear algebra. Now I'm having trouble with my grade school something. Okay, so V of A is an even function. Okay, and that means that A equals 0 is a stationary point. Okay, so we're on a roll here. Okay, that sounds good. Okay, if we make this assumption, then we're headed in the right direction, and we can in fact do better. We can do better, okay, in that we can actually calculate V of A in the following way, or V of theta. We can calculate from remembering that we can, if we think in terms of theta, we can put theta into the quark mass matrix. Okay, again, I'm trading theta regularly for A. So we have something of the form, a Lagrangian of the form e to the I theta q bar mq plus complex conjugate. Okay, so that's our Lagrangian in the presence of theta. Okay, and we know that we talked about the fact that q bar q in QCD has an expectation value, has an expectation value that's diagonal in flavor. Okay, so if we just take if we just do first order perturbation theory, okay, what are we supposed to do with first order perturbation theory? Okay, we take our perturbing Hamiltonian and we take its expectation value in the ground state in this case. Okay, so V of theta is e to the I theta, expectation value of q bar q times m. That's so q bar mq plus complex conjugate. Okay, and this is just some something proportional to cosine theta. And we want a minus, and I have a minus something of the form trace mq cosine theta lambda cubed. Okay, it's a potential which has a minimum at theta equals 0. Okay, so QCD is guaranteed, okay, in this case to preserve CP. Okay, and this is the essence of their proposal. If you go back and look at their original paper, you'll see, they were writing this at the moment Tuft was writing this complicated paper on instantons and all kinds of things, and there's a lot of, there are various complicated stories, but this is kind of the gist, except there's something else they didn't notice. When they actually wrote down a model for this, which involved two Higgs doublets. Okay, they were interested in that for some reason, and which had a symmetry which turns into this shift symmetry of A, except they didn't notice they had a light Goldstone particle. So they said, well, there's not a symmetry, there's no Goldstone, okay? But they missed the fact that, in fact, this particle is light, and you can see that here. So if I rewrite this again, we have some potential V which goes like mq q bar q. I'm just going to write it schematically. mq q bar q cosine theta. Okay, so I have a potential like this, but theta is this axion divided by Fa. And I want a minus sign here. So this is A over Fa. Okay, and so they have this particle, okay, which has a mass, ma squared, which goes like this thing, okay? And I'm not going to prove it for you here. It's kind of implicit in some of the things I've written for you. This thing goes like m pi squared, the mass of the pion squared, f pi squared. Okay? And now when we expand here, we get divided by fa squared. Okay? So they have a particle whose mass is scaled relative to the pion mass by a factor of f pi over fa. Okay. In their original model, I think as was alluded to in one of the talks this morning, I guess in Nathaniel's talk this morning, f pi over fa in their original model was not that small. Fa was of order the weak scale. So think of this as sort of a TeV. Okay? So this is the pion mass, which is of order 100 MeV, and then 100 GeV divided by 100 MeV, excuse me, divided by, which is f pi, divided by TeV. Okay, that's sort of 10,000 or so. So we're looking at, KeV kinds of, tens of KeV or tens of KeV sorts of masses. Okay, and those were quickly ruled out. They were sort of actually ruled out by pre-existing experiments, and pretty much most windows on their original model were closed. Okay, but when you look at this, what you say is, well, that's okay. Let's just make Fa big. If we make Fa big, then two things happen. One is that the axion becomes light, okay? And the other is it becomes more and more weakly coupled. Okay, so why is that? That's because of this Pache-Quinn symmetry.
How did we get that mass equation mq is squared? It should be ma squared.
Ma squared, I'm sorry. Anything else? So apart from that, I hope it's reasonably clear. I just expanded the cosine. Okay, and looked at the quadratic term. I looked at the coefficient of a squared and the cosine. Okay, here we go. So okay, so the interactions of the axion, so the mass of the axion goes as 1 over Fa. Okay, so the axion becomes light as I make Fa larger. Okay, and its interactions go like 1 over Fa. Okay, and sort of prototype for that is just the original axion coupling I wrote. I wrote something of the form A over FA, FF dual. Okay. Other, I can, so this is for the QCD FF dual. Okay, I need something separate for the electric and magnetic fields, but for the electric and magnetic fields of ordinary QED, I need some separate notation. Let me call this reversing most people's conventions. Okay, so the G and G dual here are the ordinary gauge fields of electrodynamics. Okay, and again, I have this suppression by FA. Okay, and I have similar things if I think about, and we'll talk about this in a moment, Yukawa couplings, for example, to leptons and so on. So the interactions get weaker, and once FA is greater than, say, 10 TeV or so, this axion becomes very hard to detect in accelerators. Why are they all the same? Because I'm lazy. So I can put some coefficient here. I want to be careful what I choose here. Let me call this. I think actually this is going to be called E in a moment. There's some convention for what that coupling is. So there can be a numerical. So basically, there's a sort of spirit of dimensional analysis which will hold in particular models. Okay, that there's a characteristic scale which enters. Okay, the coefficient, the detailed coefficients may depend on the model and sometimes may vanish and so on. Okay, so yeah, let me just see here. How are we doing? Yeah. All right. So a couple things. Let me write. You can write a more detailed formula. Maybe I'll take this up in the last lecture a little bit more detail. But I sort of schematically indicated what V of A looks like, or V of theta. Okay, you can be a little more careful putting in the different quark masses and so on, and you get that, for example, with two light quarks, this becomes V of A is minus m pi squared, f pi squared, square root of mu md over mu plus md cosine A over FA. Okay. And just to put in some numbers, MA is 0.6 MeV, okay, where the M now stands not for a million, but for milli, 1,000th of an electron volt, times 10 to the 10th GeV over FA. Okay, so it gets, so the axion mass, as I said, like other things, gets small linearly with FA. And then what I'd like to do is I'd like to describe two benchmark models. And okay. And these have various names attached, including mine, but I don't kind of love this this terminology. So there's something called the Dfs D Model. Okay, and this is a variant of the model that actually Pache and Quinn wrote down. It was motivated by things that came from supersymmetry. And the model contains two Higgs doublets, which I might call phi u and phi d, okay, which are going to be responsible for breaking SU2 cross U1, and they're assumed to couple to quarks and leptons like the Higgs doublets of the MSSM. Okay, and one more field, a singlet scalar, phi. Okay. each of these transforms under the Pache-Quinn symmetry as phi, for example, goes to e to the I alpha phi. Okay, phi u and phi d. Yeah, phi u goes as e to the minus I alpha over 2 phi u. Phi d goes to e to the minus I alpha over 2 phi d. Okay, the quarks and leptons transform as they have to make the Lagrangian invariant. Okay, and the assumption here is that the expectation value of the singlet phi is much greater than that of phi u and phi d. Okay, so there's a Goldstone boson that comes from breaking the symmetry, and because of the large phi expectation value, that Goldstone boson is mostly the phase of phi. So phi is some expectation value which I could call Fa, e to the I a over Fa. Okay, so the axion is mostly inside this field phi. Okay, and then you can work out in this model things like the couplings of phi to of A, excuse me, to FF dual and A to GG dual just from the anomaly diagrams. So, for example, as I say, the quarks and leptons carry various charges under this symmetry. And so if I draw a diagram where an A comes in and a pair of gluons or photons come out, okay, I can work out what the couplings are to this FF dual. And in fact, well, I think well, yeah, let's write it down. Just sort of for completeness. For some completeness, these couplings are parameterized. If you look at papers on axion detection, one writes L gamma gamma, the photon coupling, is a quarter some number GA gamma gamma, AFF dual. Just worried there's something missing. No, that's okay. Okay, and people write this GA gamma gamma. This is coming from here, this loop diagram which describes this coupling to two photons, of the axion to two photons. Okay, and this GA gamma gamma is parameterized in this way. It's written as alpha over 2 pi E over n minus 4/3 and some factor. This is kind of more than you want to see. 4 plus z over 1 plus z, 1 plus z over square root of z, ma, the axion mass, divided by m pi f pi. This goes to 0 as Fa goes to 0 because ma goes to 0. Okay, so it goes like 1 over Fa. Okay, and this thing I called z is mu over md. I'm sort of writing this down just because, say, when Peter shows you, talks about axion detection experiments, okay, these are kind of these are the parameters that are kind of the measure of the quality of the experiment, of what the reach of the experiment is in each case. Okay, so this is an example. In this case, I just wanted to write down what G was just to say that you can compute it, or this E. Okay, so this quantity E over n in this theory is 8/3. And you can work out in this theory things like the coupling of the axion to the electron. Okay, and I'll leave that for you to, if you want to, if you're hardcore, to glance at these notes. So this is one model. This is one of my these benchmark models. Okay. Sure.
Are you assuming phi, not the phi gamma, phi couples to vector like heavy quarks, or what's
No, I'm just assuming that phi. No, I'm just assuming phi couples is allowed to phi u, phi d. So, for example, I can have phi u squared if I've gotten my phi d squared. Okay, so I'm going to write down all the couplings in the potential, in the scalar potential allowed by those charge assignments.
I see. Then, in order to get that normally diagram to induce FF tilde term, are you using mixing between the?
Yes.
Oh, I see.
Yes. Okay. So another way to say this is what I can do in this. I can start with the original fields and calculate the anomaly in the Pache-Quinn current. Okay, and that's guaranteed to give this axial coupling. Okay, so another way to say it is I calculate the anomaly, so d mu j mu pq is some number times ff dual. Okay, and j mu pq in the theory with the expectation values for these fields is approximately fa d mu a. Okay, so that's a general statement about how Goldstone boson. So Goldstone bosons in general appear linearly in currents. This reflects the fact that a Goldstone boson transforms linearly under the transformation. So the commutator of the charge and the field has to give that linear shift. Okay, so what appears is something linear in the field and its derivatives. Okay. Other questions? Okay. So we've got about 30 seconds left. Okay. So let me mention one other benchmark model, and then we'll be ready to kind of take up a lot of issues in these theories next time. So the other model, I'm going to erase this parameterization and just say the other model that people use a lot is a benchmark model is the what's called the KSVZ model. Okay, and in this case, this is sort of similar to the question which was asked before. One assumes one has another vector-like quark, a vector-like quark pair with respect to the standard model. So some QQ bar, okay, with some coupling phi QQ bar, okay, with a Pache-Quinn symmetry, phi goes to e to the I alpha phi, and q, for example, goes to e to the minus I alpha q. That's my PQ symmetry. Okay. That symmetry is anomalous, again. Okay. And what you assume is that phi gets a large expectation value, breaking the Pache-Quinn symmetry. So some scale much larger than lambda QCD. Okay. And phi I can think of as being, again, FA e to the IA over FA. Okay. And in this model, I do the analogous thing. The coupling, these anomalies are somewhat different. I have slightly different couplings. Okay, sufficiently different that that this pair provides a kind of interesting range of things to search for. Okay, so these are sort of the basic models that implement this Pache-Quinn symmetry. Now, what we'll do next time is we'll think about the consequences of this model. We're going to ask what are the constraints on this FA? How large should this FA be? And one thing we'll see is that from astrophysics, FA can't be too small. Okay, the problem is that this particle is very weakly interacting. If we produce it, say, in the sun or in stars, okay, it flows out. Mostly it will flow out without interacting. It'll carry off energy. If it carries off too much energy, the stars burn out. The stars burn out too quickly. So not disrupting stellar evolution, okay, and in particular for certain particular systems like red giants and supernova 1987A, we get strong limits on FA, and we'll see that FA has to be greater than something like 10 to the 10, 10 to the 11th GeV. Okay. On the other side, we're going to see that the axions also can play an important role in the early universe. Okay, so you'll have had one more lecture, 2 more lectures, I think, from Neil by that time. Okay, so you'll know everything you need to know to follow that discussion, and we're going to see that FA can't be, at least in the conventional cosmology that Neil is describing, FA can't be too large. Okay, FA can't be larger than 10 to the 11, 10 to the 12th GeV. So there's actually a rather narrow window in terms of decades of energy where this FA can sit. Okay, if FA sits at the top of the range, turns out we produce in the early universe just the right amount of axions to be the dark matter. Okay, so I don't know how much Neil is going to say about axion dark matter. I'll have some remarks. Okay, And then what we'll do is we'll ask now, I'll come to a question I've sort of hinted at, which is, well, why should there be this crazy Pacheco symmetry anyway? Okay, why should there be a symmetry only violated by this thing in QCD? What in the world is that? And we're going to talk about how that might arise. Okay, and so just as I was critical of the mu equals 0 solution of the strong CP problem in this Nelson-Bar solution, okay, I'm also going to sort of have a critique of the Axion solution. And I'm going to talk also about some ways that it might be okay. Okay? So I'm going to give it, if you like, I'm going to give, well, I don't know, so at the moment I think at best I can give them mu equals 0 as C because I think that otherwise I will be getting in trouble with lattice gauge theorists. And maybe I'll give a B minus to the Nelson bar and I'll give a B plus in the end to the Pachequin. Okay? It won't be perfect. Okay? We'll talk about that a little bit next time. And we'll introduce some of this cosmology, and we'll talk about, where this Pacheco symmetry might come from. Okay? So, thank you. Thank you for this schedule adjustment.